You want to you want to me
Fine,
to
fine.
share my screen?
Not yet,
Not now, sir.
because
Bit later. So we'll start now. Okay.
yeah.
Welcome to this episode of Ramanujan Yatra. Today we are going to have Professor Ram Murty talking about Ramanujam. This is a program organized by Vigyan Prasad in memory of the great mathematician, internationally renowned mathematician Ramanujan. Ramanujan was born in 1887 on December 22nd, and unfortunately, at a very young age, he passed away on April 26th, 1920. This year happens to be the 100th death anniversary of Ramanujan. To recall, remember, and carry forward his legacy, and also to address the question of maths phobia, Vigyan Prasad is organizing a year-long program which began in a modest way on April 26th to December 22nd of this year. This lecture is part of this massive effort that Vigyan Prasad has undertaken. Due to COVID situation, unfortunately, all these programs are being conducted online, keeping the COVID advices in mind. We had actually had a bigger plan to reach out to mass of people through various format and various means. But given the fact of the pandemic, that we are sticking to using the web medium for going with these lectures. We have two part to this our program. One, we have lectures which is in Indian languages, and another by scholars of international repute. And today we have Professor Rama Promoti giving us this lecture. Before we begin, I would request our director, Dr. Nakur Parasar, to talk about this Ramanujam Yatra, Vigyan Prasad, and start off this program.
Well, good evening, everyone, and good morning to people on the East Coast, in Canada, in US, and a special welcome to Professor M. Ramamurthy, who has agreed to join us for this edition of our lecture today. So a hearty welcome to you, Dr. Ramamurthy, and especially a lot of thanks to my colleagues here who've initiated this idea and have gotten to this point. First, Professor Ramanujam, who's been right from the beginning, has been a person in our team who has taken this up, who started this series of lecture. The first lecture that we ever had in Ramanujan Yatra in Tamil was delivered by Professor Ramanujam of the Indian Institute of Mathematical Sciences. We are delighted to have you, sir, with us in this whole endeavor. This endeavor, as Dr. Venkateshwaran just said, we started on 26th of April 2020 to commemorate the 100th death anniversary of Ramanujan. And we thought from his death up until December 22nd, when the world, when the country celebrates uh, his birthday, Ramanujan's birthday, as the National Mathematics Day, all this while, all these months, all this period, we would have lectures from various, we'll have lectures delivered by various experts. So we divided this into two. One was a series of lectures to be delivered by experts, and a series of lectures in Indian languages. So we've so far covered Tamil, Telugu, Kannada, Malayalam, Marathi, and also Gujarati and Bengali as well. And we've also covered that in Assamese. So as we go move along, we've been through with Professor Ken Uno, Bruce Byrne, and we had Sujata Ramdorai, and now we are very honored and privileged to have Professor M. Ramamurthy with us to deliver this lecture and take us through his perception about Ramanujam. Well, there are a number of other activities that we had also planned as part of Ramanujan Yatra as well. We are trying to bring out a compilation of articles written by various people at different places in about Ramanujan. So while we go through all of this, and while we let you know what is to be done, the list is pretty long, and I think I won't try to step between you and Professor Ramamurthy now that we are all eagerly waiting to hear from him. So on this note, I thank my colleague and my friend Dr. T.V. Venkateshwaran, the person behind this entire Ramanujan Yatra. This has been his brainchild, and we've all rallied behind him to support and make it big. Arrival Palagai, the logo that you see, is a part of Vigyan Prasad's initiative for science communication, popularization, and extension in Indian languages, and particularly for Tamil. So, since this effort got initiated by a group of people that belong to Arrival Palagai, they still hold and have taken it forward. So we all support take as a part of this entire group, which has people like Professor Parthasarthi, Professor Shastri, and many other people. So have come together and have taken it forward. So with all of this, I would now request Dr. T.B. Venkateshwaran to formally introduce our speaker today and take us forward with this lecture. Over to Dr. Venkateshwaran. And once again, thanks to the entire team here at this Ramanujam Yatra. Thank you so much.
Thank you, Dr. Rakul Parasar, and we are very fortunate to have today Professor Ram Murty. I would invite Dr. Ramanujam to introduce the speaker, and the speaker will present his talk immediately after that.
Okay, thank you. It's my pleasure to introduce Professor Ram Murty, who's a friend for many years as a visitor to the Institute of Mathematical Sciences and an excellent speaker. It's great to have him here. He's a researcher in the theory of modular forms, elliptic curves, sieve theory, an analytical number theorist. He's a fellow of the Royal Society of Canada and a fellow of the Indian National Science Academy. He has received many prestigious awards in mathematics, including the Coxeter James Prize. He got his PhD from MIT in 1980, and he was in McGill University in Montreal for some years, and then he's been in Queen's University. Ram is well known for his many books, I think at least 15 books, and I don't know, he was hoping to show a few of his books today, but I'm sorry that the camera is not helping in that. But I've just, there is this great book with his brother Kumar Murty and several of other people that I know. He has books on the mathematical legacy of Srinivasa Ramanujan, which I want to particularly mention here today. There are also his books on Ramanujan conjectures and zeta functions, problems in the theory of modular forms, Hilbert's 10th problem, which is particularly dear to me. And but I must also mention that he has written books on Indian philosophy. He's a professor of philosophy in Queen's as well. So he's the distinguished professor, Queen's Research Chair in Mathematics at Queen's University. It's a great pleasure to have Ram here today. As I said, not really an eminent mathematician, he's an excellent speaker, and it's great to have him here to talk on something, especially Ramanujan's Tau function, which I think is romantic in its own way. It's great to have Ram to talk on that. Over to Ram. Ram, will you start sharing screen?
Yeah. Can you see this? It might take a while, right?
Yeah, it's come on. Yeah.
Okay, so that's the okay. Well, firstly, let me begin by thanking the organizers of the program, Vigyan Prasad and Professor Ramanujan in particular, who asked that I lecture on this topic related to Ramanujan. It's a pleasure always to be associated with IMSC and the Indian scientific community. So let me first get some blessings from Ganesha. So here is a picture of me getting blessings from Ganesha at the Kalahasti temple, which is pretty close to Ramanujan's birth. So I'm kind of fond of this picture. So the story of Ramanujan, which I want to share with you this day, is a story from rags to mathematical riches. In 1999, Robert Canigal wrote his first definitive biography of Ramanujan. So here's a picture of Robert Canigal and the book, The Man Who Knew Infinity. And I suppose Canigal was mystified, like many other people, about the equations and formulas that Ramanujan had discovered. So here's one such famous example of formula that should kind of inspire and many of us into looking at mathematics a little more deeply. How do people discover these kind of ideas and identities? So this biography is actually a pretty user-friendly biography, and it has a pretty good collection of anecdotes and tracing the history of Ramanujan to Chennai and his experiences in England and back in India again. So I would recommend this biography. It's a nicely written. So this biography inspired Hollywood to make a movie rather, of The Man Who Knew Infinity, and this is the cover of the movie, starring Dev Patel and Jeremy Irons. Dev Patel plays the role of Ramanujan, and Jeremy Irons plays the role of G.H. Hardy. And I must say, I went to see this movie rather with a skeptical mind, but I was actually impressed by the way it was done, and so would recommend this movie for anyone who is not familiar with Ramanujan's experiences in England. So let me begin with a few historical remarks. Here is the birthplace of Srinivasa Ramanujan, Sarangani Sannipadi Street in Kumbakonam. That's the place where Ramanujan was born on December 22nd, 1887 in Erode, Tamil Nadu. Here is a panoramic view of the town. You can see that many Indian towns actually had this remarkable geometry about them. You can see this kind of quadrilateral structure with temples on all the sides, giving us a certain spiritual air to the whole landscape. So the story of Ramanujan is quite inspiring by any account, and to a large extent he was a self-taught mathematician and became a universal genius with his fundamental contributions to number theory. And this talk is a panoramic view of how this came about. So there's the picture of Ramanujan's house again, in closer view. So the turning point in Ramanujan's mathematical life turns out to be this book, Plain Trigonometry by Loney. At the age of 12, he borrowed this book from an older student and completely mastered its contents. As you can see, it was written in 1893. And this book goes far beyond standard trigonometry and also treats the rudiments of calculus. So by the age of 12, he more or less mastered calculus. But the book that really made an impact on him is this book by G.S. Carr called The Synopsis of Elementary Results in Pure Mathematics. Now, this book transformed Ramanujan's life. He borrowed it from the local library and delighted in proving the results contained there. Now, the synopsis book is really not a book which explains things, but rather summarizes theorems without explaining how to get those theorems. And Ramanujan used this as a platform to teach himself on how to derive these mathematical results. But he was too poor to buy paper, and he used a slate in order to deduce the statements made in the book. And after having finished working on the slate, he would rub the slate with his elbow, having no eraser at hand. And people would often talk about his bruised elbow that he had, and we now know how he got it. He got it by erasing the slate through his childhood years. So at the age of 15 in 1903, he was admitted to government college in Kumbakonam. So here's a picture of government college. But unfortunately, he failed his exams because he spent too much time in mathematics and neglected the other subjects. It was a sad thing. So this kind of put him into a fit of depression of sorts. And then he went to Madras, having failed in Kumbakonam. In 1905, he entered Pachiyappa's College. So here's the entrance of Pachiyappa's College. And unfortunately, he failed again to his neglect because of his neglect of non-mathematical subjects. So all this kind of leads to a form of depression, and sadly, he did try to run away from home. And he, in fact, I think he went as far as Vishakhapatnam, and his father and mother, worried where Ramanujan was, put this plea for help in the newspaper. A missing boy, they say. Kindly insert this into your widely circulated journal. A Brahmin boy of the Vaishnava Tengalai sect named Ramanujan, of fair complexion, age about 18 years, was till recently a student of the Kumbakonam College. He left his home on some misunderstanding. His guardian is very solicitous about the boy's returning home. He stayed at Rajamundry for about a month and was last seen there some 5 days back. Those who happen to see him are kindly requested to persuade him to return home and to communicate his whereabouts. Srinivasa Raghava Iyengar, Sarangapani Sannidhi Street. So that's the father putting this ad on September 2nd of that 1905. The interesting thing is, in those days, Tamil Nadu, Andhra Pradesh, all of these were considered one presidency of sorts, one giant province, and people were multilingual, and Ramanujan was fluent in both Tamil and Telugu. So Rajamundry, which is in Andhra Pradesh now, and Vishakhapatnam as well, he was fluent in Telugu, so he must have had no problem in communicating with people in that faraway cities. So finally, he comes back after a month, and as a clerk in the Port Trust office, takes a job. So having failed to earn a college degree, Ramanujan accepted a job in the Port Trust office as a clerk. He also tutored students in mathematics and somehow eked out an existence. But he found leisure to do mathematics and jotted down his results in his famous notebook. So here's a picture of notebooks, his two notebooks. If my camera was working, I was planning to show you the production of the Tata Institute of Fundamental Research in the 1950s managed to publish Ramanujan's notebooks, and they are very instructive. And you would see, if you leaf through these pages, that Ramanujan was essentially teaching himself in a systematic and organized manner. He even had titles of chapters, so you would think that somehow this was his book of learning, as it were, from which he would synthesize, distill the quintessence of his learning so that he could refer back to these notebooks again. What we can learn from Ramanujan's notebooks is actually a method of studying. Even a genius such as Ramanujan relied on note-taking. And to this day, I think this is a very important aspect of learning. There's nothing better to kind of impress upon the mind the necessary facts of learning than simply writing it down. That very act allows one to have some sort of neurological understanding, which will later come on to help you in higher research. So these are Ramanujan's notebooks. I believe they're now sitting in a museum dedicated to Ramanujan in Chennai. Now, two Indian mathematicians in Chennai were very helpful and useful, and these were two men, Ramachandra Rao on the left and Narayana Iyer, manager of the Madras Port Trust. The interesting thing about Narayana Iyer is that he was also the founding father of the Indian Mathematical Society, and so both of these people felt the importance of having a society dedicated to mathematical thought to bring all the people in India together to have a share in books and journals. And so we see the inception of such an idea, and these two mathematicians having an important role in the life of Ramanujan. So Ramachandra Rao and Seshu Iyer both helped Ramanujan and discussed numerous mathematical ideas with him in 1910. I mentioned this because many people are under the mistaken impression that there was no one in India that understood Ramanujan, and so he had to go to England and communicate with Hardy. But the story is far from the truth. The fact is that many mathematicians in India did understand parts of Ramanujan's work, and it was Iyer who suggested to Ramanujan that he write to G.H. Hardy and other mathematicians. And I will talk a little bit more about this in the next few slides. So Ramanujan's work was first shown to M.J.M. Hill. So here's a picture of M.J.M. Hill. So several British professors in India showed some of the work to Hill. Looking at Ramanujan's work on divergent series, Hill remarked that he has some taste for mathematics, that is, Ramanujan has some taste for math, but should study more, and so recommended a few books. And the most important book that he recommended was Bromwich's Theory of Infinite Series. So this kind of dismissal was a little depressing for Ramanujan. So two other mathematicians were consulted, Harold Frederick Baker and E.W. Hobson. Here is Baker and here's Hobson. These two mathematicians were considered the giants in the field of analysis at the time, and they were both consulted, and neither of them actually responded to Ramanujan. Baker was undergoing a divorce and trying to enter into another marriage, and probably felt Ramanujan's letter to be an intrusion and probably did not reply on that account. I don't know the details of why Hobson did not reply. So here we have two more cases of missed opportunities. So Ramanujan's famous letter to G.H. Hardy was dated 16 January 1913, and it was a turning point. After a brief introductory paragraph, the letter lists theorems and formulas for the next 10 pages. Can you imagine getting a letter 10 pages long, and every line is a formula? So here's G.H. Hardy, and here is the opening first page of Ramanujan's letter to G.H. Hardy. Very beautifully written, actually. If you see the handwriting, it's absolutely spectacular. Very legible, even here. And it's a beautiful letter. So here are a few sample pages from the letter. Now here, these have been printed in, I was going to show you again, prop number 2, collected papers of Srinivasa Ramanujan. I was going to hold in full view my proud copy of collected papers of Ramanujan, which I had bought in India for a mere price of 1,000 rupees, which is not bad. Oh, sorry, 500 rupees, which is not bad for the wealth of knowledge it contains. So in this collected papers of Ramanujan, you see printed aspects of his letter. Here are a few formulas you can see, and these are formulas, remarkable formulas actually. Let me draw your attention to a few of these. So formulas, and Hardy received this letter, and he lost sleep over it actually. He couldn't decide if it was written by a genius or a crank. There were 120 theorems stated in a single letter. I must tell you that if a person proves 120 theorems in an entire lifetime, that would put him on a very high scale in the contributions to mathematics. Here we see 120 theorems in a single letter. Now I want to draw your attention to this particular formula number 7, because this formula 7 will appear later in our discussion, and I just want to highlight that so that you understand what it is. It's talking about the coefficient of a particular power series being given in terms of hyperbolic cosine and hyperbolic sine, and this will appear later. Here are a few more extracts from Ramanujan's letter. So here's the 16 January letter. These are the kind of formulas that confronted Hardy when he looked at the letter. Here's another page. That's all. I mean, there was no prose in between these formulas. It was just formula after formula. And to the initiated, of course, they're extremely intriguing. And one could only wonder, how did you get these? Here's another page. 17 February 1913, Ramanujan writes this letter, second letter. See, these are kind of formulas that are in there. Formula for pi, a formula for e to the pi, root 58 being very close to an integer. And let's look at this letter a little closely. This formula actually was discovered by Riemann 50 years earlier or so. Ramanujan couldn't have possibly known it, but he seems to have derived it on his own. So Hardy's initial reaction, here's Hardy. Next to him is Littlewood. So this is the famous Hardy-Littlewood pair. So after losing sleep that night, Hardy invited his colleague, Littlewood, to come over and have a look at Ramanujan's letter. So Littlewood came over to Hardy's apartment around 9 p.m. They spent more than 3 hours looking at Ramanujan's letter and finally concluded it was the work of a genius. Hardy's response: a single look at them, he says, is enough to show them that they could only be written down by a mathematician of the highest class. They must be true, because if they were not true, no one would have the imagination to invent them. Quite a remarkable certificate of endorsement. The next day, the whole of Trinity College was abuzz with this new news. So here's Bertrand Russell, who says that the next day he found Hardy and Littlewood in a state of wild excitement because they believe they have found a second Newton, a Hindu clerk in Madras making 20 pounds a year. So after about a year's of correspondence back and forth, G.H. Hardy realizes that it's good to bring Ramanujan to England, so he engages Neville, who was going to India to give lectures, to try to convince Ramanujan to sail to England. So on the 17th of March, 1914, he set sail to England and arrived there on 14th April, 1914, after almost a month. And of course, he was seasick for a period of time. So this is, remember that the first letter to Hardy was written January 1913. After that, they exchanged about half a dozen more letters. And through that correspondence, Hardy was convinced that it would be profitable to bring Ramanujan to England because they could collaborate. And of course, Ramanujan, in his earlier letters, was not seeking any invitation of any sort. All he was asking was for someone who could share in the mathematical joy of his discoveries, which he found in a personage such as G.H. Hardy. And in fact, that correspondence led him to get a scholarship, and he was back to normal with respect to his monetary needs, and was doing his research for more than a year. It was only when Neville went to India to give those lectures in differential geometry at the University of Madras that Hardy had asked him to make a plea on his behalf to convince Ramanujan to come to England. The interesting thing is, for Orthodox Brahmins, it was taboo to cross the seas, and the strange permission seems to have come in a dream to Ramanujan's mother, who had the vision of goddess Namagiri, who said that she should not stand in the way of Ramanujan fulfilling his mathematical destiny. And so the permission came in this kind of divinely inspired way. So this is a very remarkable period. He was received by Neville in London, with whom he stayed for a few days before taking the train to Cambridge. He stayed in England for 5 years and returned to India in 1919. Unfortunately, he died a year later at the age of 32 in 1920. So here's a picture of Neville. So he was the person who was instrumental in arranging for Ramanujan to come to England. And he received him in London, and Ramanujan stayed at their house for a couple of days before going to Cambridge. Now, Ramanujan's work in England is very productive. It's amazing. It's 1914 to 1917. The backdrop, of course, is World War I. Hardy and Ramanujan had fruitful collaboration during this 3-year period, and during that time, Ramanujan wrote over 30 papers, 7 of them jointly with Hardy. 30 papers in a span of 3 years is about 10 papers per year. That's a very productive period of research. So we'll highlight here 3 of these papers since they shaped the course of 20th century mathematics. So the 3 fundamental papers that I want to kind of focus on are the paper concerning the normal order method. Don't worry if you don't understand everything. The sense will come through, hopefully. And so for some of you who are technically proficient, they may get some inspiration to study some of this stuff more. The circle method, paper in 1918, and the famous Tau function paper written in 1916. So these are the 3 papers I want to kind of focus on. Of the 30 papers he wrote, let's look at these 3 papers and see where mathematics went with respect to these ideas. So what I want to do is first tell you what each of these papers contained, and then describe the developments after that. So it's almost like a giant banyan tree that kind of spreads out its multifarious branches, and you can see that each branch has a new contribution for the rest of mathematics. So the normal order method deals with the function omega of n, which is the number of distinct prime divisors of n. Most of you know that every natural number can be written as a product of prime numbers in a unique way, and omega of n counts the number of distinct prime divisors of n. So omega of n is equal to 1 if and only if n is a prime power. And the question that Ramanujan and Hardy had asked themselves is there any regularity in the behavior of omega of n? And Hardy, the Ramanujan theorem is that omega of n is usually log n. And so the question is, what is the meaning of that? Is somebody's microphone on or something? I'm hearing some other background noise. Is it possible to? Okay, is it possible to yes, to shut off any other microphones, please? So this is the theorem Hardy and Ramanujan. Omega of n is usually log n. And so let me try to explain that in a little bit more detail. The number of numbers n less than x, such that omega of n minus log n is bigger than square root log n, is little o of x as x tends to infinity. Now, if you don't understand that, let's just understand it in the following way. With probability 1, omega of n is usually log n. Now, this theorem inspired many other theorems. In fact, it inspired a whole new branch of mathematics called probabilistic number theory. And it was innovative for its use of the rudimentary sieve method. In 1940, for example, it inspired erudition cats to try to see if there was some sort of connection between this theorem and the normal distribution. As most of you know, the normal distribution seems to pop up everywhere. It seems to be an ubiquitous phenomenon in mathematics and in life in general. And this density function is given by this integral a to b e to the minus t squared over 2 dt over root 2 pi. And this particular theorem of erudition cats, so here's a picture of erudition, here's a picture of cats, it led to the creation of this new branch of mathematics called probabilistic number theory. So you see the 1916 theorem on the normal order method led to the 1940 theorem of erudition cats. And to this day, we have some further developments. So let me try to share a few of those further developments here later on. Now, the second paper is about the partition function that I want, the circle method. The function p of n is the number of ways of partitioning n. So let's have an understanding what this means. The number 4 can be partitioned as 1 plus 1 plus 1 plus 1. Or it can be partitioned as 1 plus 1 plus 2, or it can be partitioned as 2 plus 2, or 1 plus 3, or 4. So the total number of partitions, we don't worry about the ordering, we just worry about the pieces. The total number of partitions then is p of 4 is 5. Now, this shouldn't be too hard because in that Hollywood production of The Man Who Knew Infinity, surprisingly, there is a 5-minute segment in which the partition function is actually defined. So, which is quite a feat for a Hollywood production, giving some non-trivial mathematical descriptions. So now each partition can be factored as k1 plus 2k2 plus 3k3 and so on and so forth, where ki's are the number of times each I occurs. And for a little bit of mathematics, you can see that it has a generating function given by summation p of n x to the n by a product k equals 1 to infinity, 1 over 1 minus x to the k. Now, can we find a formula for p of n? So in 1918, Hardy and Ramanujan discovered, using his famous circle method, the asymptotic formula that p of n is usually e to the pi square root 2n over 3 divided by 4n square root 3. Now, before I continue, let me just say that the partition function has now found numerous applications, not only in mathematics, like group theory, study of the symmetric group, and so on and so forth, but also in physics. So the partition function seems to be something which is fundamental in the nature of things, because physics seems to have embraced it and uses it quite widely. Now, in 1937, Rademacher derived an asymptotic expansion for p of n. So this is an asymptotic formula, which will, in some sense, gives the first term. But Rademacher, working 20 years later, found this remarkable formula, exact formula, as you can see here, p of n equals 1 over pi root 2 summation k going from 1 to infinity root k ak of n times d by dn, this hyperbolic sine function. And what are these functions? These functions are ak of n is given by an exponential sum, and the quantity in the exponent is what is called a Dedekind sum. Looks very complicated. Don't worry about it, but understand that there's a beautiful explicit formula that seems to have come out. And surprisingly, Ramanujan knew this. And in his first letter to Hardy, he was trying to say so. So let me try to highlight that aspect. Let's look at Ramanujan's first letter. So you will recall that I flashed this picture giving formulas. And this formula right there, involving hyperbolic sines and cosines, is an indicator to us that somehow Ramanujan knew that you could probably get explicit formulas of this nature. And so sadly, they seem to have missed that and settled for an asymptotic formula instead of an explicit formula. And Selberg, Atli Selberg, a famous mathematician of the 20th century, here's a picture of Atli Selberg. He writes that in the summer of 1937, I had actually myself been studying number 36 in the collected papers of Ramanujan and had arrived at Rademacher's formula. It always seemed strange to me that Hardy and Ramanujan did not end up with this formula, and I believe firmly that the responsibility for this rests with Hardy. It's an interesting statement, and partly funny, actually. And for those of you who know Selberg, this is a very critical assessment of the situation, and it has to do with the fact that Hardy was basically an analyst and Ramanujan was basically a number theorist. And so even though they could communicate and talk to each other on related formulas and related problems, the perspective that each had was slightly different. Hardy, being an analyst, was always looking for asymptotic formulas. Ramanujan, being a number theorist, was trying to understand the structure of things and therefore was seeking more explicit formulas. Now, in January 2011, so it's relatively recent, less than 10 years ago, Brunier and Ono, Brunier and Ono discovered an exact formula. So here's Brunier. So this is a picture of myself with Brunier, Ono, Youngju Choi, Winfried Konen, and I forgot the Japanese mathematician's name, but it'll come to me. And we were there teaching, giving a course on modular forms, and well, Kaneko, Masabu Kaneko, sorry about that. So Kaneko, there's Ono, and there's Brunier. They both discovered an explicit formula for P of n in terms of special values of the weak mass form evaluated at CM points in the upper half plane of discriminant minus 2, 4, n plus 1. So this is an interesting new derivation, which was not known at the time of Ramanujan. But this formula gives us another algebraic connection to the partition function. And so this allowed me to get interested. And so with my postdoctoral fellow, Michael Dewar, and myself, without using the circle method, we managed to show that the partition function has this asymptotic formula. So this is a new way of deriving the same thing without using the circle method. So this is, again, one of these branches of the banyan tree, starting with this original idea almost a century ago, leading to these new ideas connecting mock modular forms. So the generating function for the partition function can be defined as given by this thing as I explained, and this is a connection between modular forms and the partition function. If you put x equals e to the 2 pi I z, the right-hand side becomes x to the 1 over 24 divided by eta of z, where eta of z is the Dedekind eta function. Eta of z is a modular form of weight 1/2. This means that if I transform the function using fractional linear transformations, you get essentially c tau plus d to the half eta of tau, and then there's this factor, epsilon factor, which is a little complicated, which I'll not get into. But the ABCD has to be a member of SL2C. Now we come to the third paper. So Ramanujan's conjecture and the theory of modular forms. This theory has its origins in the 1916 paper that I mentioned, outlining the properties of the tau function. Now, the tau function had been studied after Ramanujan had introduced it by Louis Mordell, Eric Hecke, Joseph Lehner, and Atkin. And these people developed the theory well into the 1960s, from early 1920s to 1960s. And so you can see, again, another almost a half a century of work emanating from this 1916 paper. So what is this tau function and what is this delta function? Well, you can write down this product. So let me just point this out. Take this infinite product here, q times product 1 minus q to the n to the power 24, and expand it, and the coefficient of q to the n is then tau of n. Ramanujan wrote down the first bunch of coefficients. He wrote down, I think he wrote down more than 30, but people say he certainly wrote down the 30. And remember, he was working on a slate, so it's very hard to cram these huge numbers onto a slate. But nevertheless, he did do it, and he had probably, formidable memory, so he could remember these things. Now, normally when you or I are looking at these formulas, we see nothing except huge numbers. But for a mind like Ramanujan's, he would see patterns immediately. For example, if you take the second coefficient, which is minus 24, and multiply it by the third coefficient of 252, you end up getting 6,048. Ramanujan noticed that. If you take the second coefficient and multiply it by the fifth coefficient, you get the 10th coefficient. And so he would go on noticing patterns in these numbers. These numbers were not just random numbers. They had a certain pattern. And what were these patterns was the question that occupied Ramanujan's mind. So he made these conjectures that tau is a multiplicative function. So when I said the second coefficient times the third coefficient to the sixth coefficient, I'm telling you that there's a multiplicative property. And so he would say that there's a more general pattern. Tau of mn is always tau of m times tau of n, whenever m and n are co-prime, which means they don't have a common prime factor. Then tau satisfies a second order recurrence relation for prime powers. It's a little bit more complicated, which I will not get into right now. And then for a prime p, the tau of p is always less than 2 times p to the 11/2. So these were the three famous conjectures of Ramanujan. There are more conjectures, but we'll come to those later. But these are called the Ramanujan conjectures. They were formulated by him in 1916. And the first two conjectures were proved by Mordell shortly thereafter. But the third one was a difficult one, was finally solved in 1974 by Pierre Deligne, who got the Fields Medal, which is the mathematical equivalent of the Nobel Prize, for this work. Now, Deligne was working on another set of conjectures, which I will explain, called the Weil conjectures. And those were the conjectures that were linked mysteriously, unbeknownst to the mathematical community, to the Ramanujan conjecture. So that's another interesting story, which I hope to captivate you in the next 5 minutes or so. So let's get back to Hardy on the Tau function. Hardy, in his 1936 lectures on Ramanujan, delivered at Harvard University, made some comments about the Tau function that have become famous, or infamous, shall we say. Anyway, he said that we may seem to be straying into the backwaters of mathematics, but the genesis of tau of n as a coefficient is so fundamental a function compels us to treat it with respect. And so Andre Weil pounces on this comment. In his 1972 Rit lectures, Weil makes several pronouncements on what analytic number theory is, and then pounces on Hardy. He wrote, Hardy's a remarkable comment is we seem to have drifted into one of the backwaters of mathematics. To him, it was just another inequality. He found it curious that anyone could get deeply interested in it. In fact, he becomes apologetic and explains that in spite of the apparent lack of interest in this problem, it might still have some features which made it not unworthy of Ramanujan's attention. Well, how did Weil come to make his famous conjectures, which apparently, unbeknownst to him and unbeknownst to others, were secretly connected to Ramanujan's conjectures? So he says, in 1947 in Chicago, I felt bored and depressed. And not knowing what to do, I started reading Gauss's 2 memoirs on biquadratic residues, which I've never read before. The first one deals with the number of solutions of ax to the 4 minus by to the 4 equals 1 over finite fields. And the second one with ax cubed minus by cubed equals 1. Then I noticed similar principles can be applied to all equations of the form ax to the m plus by to the m plus cz to the r plus ... equals 0, and that this implies the truth of the so-called Riemann hypothesis for diagonal equations. So this is how Weil realized and formulated his Weil conjectures. He was looking at something completely different. And it just happens that it's connected to Ramanujan's conjecture, and the key idea is a conjecture of Sayre, that there exists a Galois representation. So GQ here is the absolute Galois group, and it's a representation into GL2 of the Aladic integers, such that the trace of the Frobenius automorphism of this representation is tau of p. Now, of course, I don't expect all of you to understand what I'm saying. Let me try to explain it in simple lay terms. This particular conjecture of Sayre gives an algebraic interpretation of the tau function. It tells you the tau function, which was defined combinatorially by Ramanujan, is actually has a deeper meaning. The deeper meaning comes from algebra, and this is the significance of this particular conjecture. Now, Deligne proved Sayre's conjecture and related to the Weil conjectures, and thereby showed Ramanujan's conjecture is true as a consequence of the Weil conjecture. So it's a kind of a very roundabout, almost a century. Well, not exactly a century. I would say maybe, what, 60 years? Yeah, 60 years between 1916 and 1976, in which the conjecture got solved. The existence of that particular representations opens the door to study divisibility properties. So many things can be done. How many prime divisors does tau of p have? So you can try to relate the normal order method of Hardy and Ramanujan to study the normal order of the number of prime factors of tau of p. Then there's another famous conjecture about tau of p never vanishing. This is called Lamer's conjecture. It's still open. Then there's the other conjecture, are there infinitely many primes? P says that tau of p is divisible by p. This is also quite open. And so, but now that we have an algebraic understanding of tau of p, maybe there's a way to approach these things. And indeed, some new approaches using the theory of mock modular forms have been suggested by Ono and others in the recent past. The Erdős-Katz type theorem for tau of p can be studied, and this is what Kumar, Murty, and myself have done in the 1980s. So we proved that the number of primes p less than x, that omega of tau of p usually is around log p, is asymptotic to this prime numbers, and now we get the same normal density function. And unfortunately, we had to assume the generalized Riemann hypothesis, which of course I will not explain here, but suffice it to say so. Here's a picture of Kumar. Here's a picture of myself. So we proved this in the 1980s. And deeper aspects of the Tau function have been explored, and the famous conjecture of Sato, Mikio Sato, and John Tate, and modified by Jean-Pierre Serre, says that the Tau function divided by 2p to the 11 half is equidistributed with respect to this funny measure called the Sato-Tate measure. And this was an open problem for a long time until recently it was solved. But let me talk a little bit before I talk about the horizontal Sato-Tate conjecture, which was what there was. Let me talk a little bit about the vertical Sato-Tate conjecture. This was formulated by Serre in 1997. He proved that if you fix a prime p and consider the normalized eigenvalues of all the Hecke eigenforms of weight k and level n, these are equidistributed with respect to a modified measure, some sort of mu p. And in joint work with my former student Kanika Sinha and I in 2009, we managed to get an error term on this result, log p over log km. Kanika is now a professor at IISER Pune. So this is the development of Ramanujan's thought up to essentially the 21st century. So what about the classical Sato-Tate conjecture? Well, Barnett, Lamb, Garatti, Harris, and Taylor published a proof of this conjecture. This is a remarkable achievement of the 21st century. And the result applies to Fourier coefficients of Hecke eigenforms, uses representation theory, algebraic geometry, and number theory. And that's a big achievement. And it allows us to talk about how big and how small can tau of n get. The reason I point this out is because this particular problem of the maximal order of tau of n is something that I was excited about in my early days, and I recall thinking about it in the library of the Tata Institute back in 1981, looking outward to the vastness of the Arabian Sea. I was thinking that something can be proved. In fact, what I proved at that time was that tau of n over n to the 11 halves is less than exponential constant log n over log n, and the constant should be log 2, but at that time I couldn't prove it. But now with the Sato-Tate distribution finally resolved, you can actually prove this theorem. So you can see that almost a century later, the conjectures of Ramanujan are still being researched and new things are being discovered. More things can be said about a Chebotarev Sato-Tate style type theorems. And modifying the arguments of the BGHD paper, we see that twisting by Art and L series, you can derive the non-abelian version of the classical Chebotarev density theorem. And this is joint work with Kumar Murty. So let me now return, having described Ramanujan's work and how it has developed over a century with the 3 papers. Let me talk a little bit about Ramanujan's illness at the very end of his life. So in the spring of 1917, he contracted tuberculosis, was admitted to a nursing home in Cambridge, England. And he showed some improvement in the fall of 1918, and he was elected to the Royal Society at that time. But early in 1919, he recovered enough to return to India and shortly afterwards passed away on 26 April 1920 at the very, very young age of 32. And the famous number 1729, most of you might know about it, has an interesting history. It's connected to this taxi cab. When Ramanujan was ill in the sanatorium, Hardy came to visit him in a taxi with number 1729. On entering the room, Hardy remarked, "I just came in a taxi numbered 1729, which looks like a dull number. I hope it is not a bad omen." And Ramanujan immediately said, "On the contrary, it is very interesting. It is the smallest number that can be written as a sum of 2 cubes in 2 different ways." Well, what are these ways? Well, 1729 can be written as 1 cubed plus 12 cubed and 9 cubed plus 10 cubed. And it's the smallest number that can be written in 2 different ways like this. And Ramanujan knew it right off the top of his head. Well, how does one know this thing? Well, it should have not been a surprise to Hardy, because if you look at the function delta that we talked about earlier, 1728 appears in the denominator. And so 1728 is not a number unknown to anyone who works in modular forms. And so Hardy's comment is a little out of place. The interesting thing is 1728 also occurs in the Indian Puranas, in Patanjali's Yoga Sutras, for example, and in the Kurma Purana, 12 times 12 times 12, 1728, is the number of seconds of focused concentration, according to Patanjali, that one needs in order to get enlightenment. That works out to about less than half an hour. So this 1728 and 1729 are numbers that seem to be steeped in Indian philosophy and Indian mathematics. And on his deathbed, Ramanujan talked about Mach theta functions and Mach modular forms. And in his last letter, described a theory, and it took mathematicians 80 years to formulate precisely what Ramanujan meant by these functions. And in modern language, Mach modular forms fit neatly into an exact sequence. So if you think about script m sub k, the Mach modular forms of weight k, then they fit into the sequence of m sub 2 minus k's modular forms of weight 2 minus k, the classical modular forms. M sub k shriek is essentially the classical modular forms, except now you are allowing for poles to exist at the cusps. So in the case of classical modular forms, you expect everything to be holomorphic, but now you want poles of finite order at the cusps. So this gives you a very interesting decomposition. And if my camera was working, I was going to show you this remarkable book by Catherine Bringman, Amanda Folsom, Ken Ono, and Larry Rowland, published by the American Math Society, which talks about the theory of Mach modular forms, which is some book that you can perhaps learn this new theory from. So this map that goes from, so every F has a decomposition H plus G star. This G star is what S of G star is called a shadow map. It maps the Mach modular form into classical modular forms. It's an interesting idea of a shadow map. So Mach theta functions are Mach modular forms of weight 1/2. So these were the functions that were discovered by Ramanujan on his deathbed, literally. So Hardy thought that all was well on 12th January 1920 when he had received this letter from Ramanujan describing his new discovery of Mach theta functions. They are now subjects of current research, and I talked already about the Brunier-Ono work. And Freeman Dyson says that these things probably are pointing to a new theory, tantalizing hints of a grand synthesis still to be discovered. It should be possible to build them into a coherent group theoretical structure analogous to the structure of modular forms, which Hecke built around the old theta functions of Jacobi. This remains a challenge for the future. So let me come back to Hardy and Ramanujan. As you know, Hardy was the only person who had the presence of mind to respond to Ramanujan's letters. And in 1936, he kind of reflects back, looks back at that moment in his 1936 letters. He says, I have to help you to form some sort of reasoned estimate of the most romantic figure in the history of mathematics. The real difficulty for me is that Ramanujan was in a way my discovery. I did not invent him. Like other great men, he invented himself, but I was the first really competent person who had a chance to see some of his work, and I can still remember with satisfaction that I could recognize at once what a treasure I had found. I mean, we could kind of imagine ourselves back to that night in Cambridge when he lost sleep trying to figure out who Ramanujan was when he was looking at his letter. And so he adds, and my association with him is the one romantic incident in my life. It's certainly something that we can identify with. So here is Ramanujan's story. Here are his contributions. I hope I have given you some sense of the life of Ramanujan, both as a human being and as a person who contributed to the richness of mathematics. And let me finally end this by a quote from Aurobindo. and which seems to be quite appropriate to the life of Ramanujan. On a height he stood that looked towards greater heights, our early approaches to the infinite, our sunrise splendors on a marvelous verge, while lingers yet unseen the glorious sun. What now we see is a shadow of what must come. So this is from Aurobindo's 2-volume poem called Savitri. So here is the picture of the glorious sun, and I thank you for your attention.
That was excellent, sir. That was really excellent. Now I would request Dr. Ramanujam to come in and carry on with the questions. Perhaps we can also share a photograph of the speaker. For some technical reason, we couldn't get his direct image. So,
okay, so let me. One moment, I'll share screen. And, yeah.
Should I stop sharing screen?
Yeah. Yeah.
Okay,
Please,
the speaker can stop sharing the screen.
Well, this is Murty for those who missed. Maybe I can start the questions, TV? Yeah? Yeah, so I have a question.
Yeah,
we were
please,
talking
please.
about the Tau function, and so you were using the delta function, right? The Weierstrass delta function. So was it the case that Ramanujan was interested in the theory of elliptic functions, elliptic integrals or curves, or I don't know, did he get interested in complex analysis? Was there any connection with these? Because, and also, did he look at Q series, modular forms? How did he get to this Tau function? Which was the kind of route that he arrived at?
Yeah. So very good, very good question. So in some sense, he studied Jacobi. He was in some sense a successor of Jacobi, who dealt with Q series and combinatorial questions. And one of the things that he knew that, if you remember, I had talked about the eta function, and the eta function was a modular form of weight 1/2, and it had this epsilon factor, which was a 24th root of unity. And so what he knew was that if you took the 24th power, you get rid of that 24th root of unity. And so 24 seemed to be the nice thing in order to get a nice transformation rule. So that's where that 24 comes from. And then, of course, it's also related to trying to write a number as a sum of 24 squares, and tau then turns out to be the error term. So in that sense, there were some combinatorial questions coming from the theory of Q series as well, although it was never formulated as a Q series thing because that terminology wasn't there at the time. But this was going back to the work of Jacobi, and I believe that's the reason for looking at the 24th power, to get rid of the 24th root of unity.
Thank you. What about elliptic curves, and did he work on elliptic functions in general?
He certainly worked on elliptic functions, but he didn't work on elliptic curves. So that kind of comes later, but that classical theory of elliptic functions, theta functions, and whatnot is certainly something he was quite familiar with. Yeah.
Thank you. Over to TV.
Yeah, thank you. See, there is one question from Mr. Bharadwaj, Mardesh Bharadwaj. He is asking that what made Hardy see a special thing in the paper, in the letter that he received from Ramanujan?
Well, that's a very good question. In some sense, that question is delved deeply in Canigal's book. And his comment is that the other people, Hill, Hobson, Baker, these people were of an older generation. And Hardy was only 35, I believe, or thereabouts, when he received Ramanujan's letter. So he was not that much older from Ramanujan. Secondly, he didn't make a snap judgment about the letter. Instead, he let the letter sit, and he was trying to think about it, and then tried to prove a few of the formulas that Ramanujan had, and was getting difficulty proving it. So then his interest and curiosity was piqued by this letter. And so then he brought in Littlewood, who's, I would say, of equal stature. So here you have two of the greatest mathematical minds of the early 20th century looking at this letter from Ramanujan and not dismissing it for more than 3 hours, losing sleep over it, and well into the early hours, wee hours of the morning, finally saying, yes, this is the work of a genius. I mean, that's a kind of a very exhilarating moment, isn't it? I mean, we can kind of go back in time and imagine ourselves in that very room and share that excitement of Hardy. And I think he is certainly justified when he says that he, in some sense, discovered Ramanujan. I think he can take some credit for that. I'm what I'd like to see, and I don't know whether anyone's done this research or not, is I would like to see what did Hobson, Hill, and Baker say after Ramanujan had achieved his, what did they say about their own missed opportunities? That would be nice to see. I did comb through the book of Canagle to get a hint of that, an answer to that question, but I didn't get it. It would require, I don't think it would require too much research, but it's an interesting theme to follow.
So the same person had another question. This one is about how did Hardy feel about Ramanujan's letter, but how did Ramanujan feel about Hardy after meeting him and working with him?
Okay, that's a very good question too, and that question is answered to some satisfaction in Canagle's book, because the first reaction, of course, you see, that Ramanujan gets, he actually gets an answer back. He gets an answer back which says, these are interesting. Can you show me your methods? How are you getting them? You know, so there all of a sudden he finds somebody has opened, a friend to talk to, as it were. So he immediately realizes in his February letter, 1913, he says, I'm really happy to find a friend in you who can understand these things. And I think this is an amazing idea. You see, actually, our human species are a kind of social creatures, actually. We need other people. And I think this COVID-19 is bringing this point very much home. We actually need the interaction between ourselves, other people, other friends, and conversations, a little bit, that dialogue. I think we're interconnected. And that interconnectedness is certainly being brought home here. Finally, Ramanujan sees that he's got somebody he can connect with. And that leads to an exchange of at least more than half a dozen letters during the course of 1913. And then only, as I said, Ramanujan never had any intention of going to England. It was Hardy who starts suggesting that he should come there. And that's the beginning of this whole remarkable story.
Yeah, that's nice. There is one Vinay Kumar. He had asked one question that how do you see mathematics and nature interconnected? What does mathematics tell about nature?
Okay, that's a very good question. The idea that nature and mathematics are connected is an idea that goes back even to far back to the prehistoric times, as it were. The whole idea of number, and for example, the Pythagorean theorem, or the theorem as we now know, recorded in the Sulva Sutras. So many cultures and civilizations had discovered what is now called the Pythagorean theorem. The Pythagorean theorem tells you that if you have a right angle triangle, the sum of the squares of the two sides is equal to the square of the hypotenuse. And Pythagoras kind of evolved a religious cult out of that, because for him that theorem was something bordering on the religious, in the sense mystical, because it didn't matter what right angle triangle you took, there was always this relationship between the sides and the hypotenuse. So he felt that there was some mathematics in nature. Music, for example, is also, why is it that we have these notes, sa, re, ga, ma, pa, da, ni, sa? These are notes which are given numerical value. And that sense of harmony that seems to exist in nature is something that is brought about again by numbers and mathematics. And of course, Galileo said the language of God is the universe is written in the language of mathematics. And these are again, when people like Isaac Newton discovered the law of universal gravitation, they realized that there's some sort of underlying law in nature that can be described at best by mathematics.
Yeah, that's nice, sir. There is one more question which will just come on the screen in a minute. Yeah, it's come on there. I mean, Kaushik. Other than 24, is there similar theory like tau function?
Yeah, well, that's a good question. Yeah, and that's what's called the theory of modular forms. Yes, indeed. If we stick with the Dedekind eta function and take higher powers of the Dedekind eta function, we'll get functions which are very similar to the tau function, which Ramanujan actually studied. But moving away from the eta function, the whole theory of modular forms is studying functions like the tau function. And that's what's called the theory of modular forms. So that explains it. Yeah.
So we'll have the next one. Next one is by Kuldeep Kumar. Sri Kumar, sorry, Akash Gupta. Okay, yeah. Sir, did he work on standard normal distribution too?
Yeah, that's a good question. No, he did not. I don't think Ramanujan knew anything about the normal distribution, but he was certainly working through things which seemed to suggest that there was a connection, but he himself did not work on the standard normal distribution, nor did he have any idea about linking number theories to statistics.
Yeah, we can go to the next question. Kuldeep Kumar. Yeah, did he believe in some deity? And I mean, there is a story that he asked deity, and then for any typical query, he got the answer. Is it true?
Okay, this question now, this is where I differ from Kanagal. Okay, so I will tell you first what Kanagal says, and then I will tell you what I think. Kanagal seems to like this idea that he got inspiration from a deity. The goddess Namakal, Namagiri, and so on and so forth. But being a Kanagal is not an Indian. He's an American, and now me being an Indian and being well acquainted with the Indian psyche to some extent, hopefully my own psyche, I know that we in India we always used, oh, this is all Bhagavantud Leela. Anytime we can't explain anything, you just say this is all the play of God, which is basically I don't know anything, and neither does anybody else. So we know that there's something larger than ourselves, and that's true. Anybody worth the name, whether they're a creative artist or a scientific mathematician, we know that there are mysterious things in the world that we don't understand, and because we're overwhelmed, we just say, yes, the goddess inspired me. How did you get this new idea? Well, the goddess inspired me. Of course, in some sense, that's true, for lack of a better explanation.
Yeah, fine, sir. There is a next question. Why did Srinivasa Ramanujan come to Cambridge University in 1914? Did he add any links with them with the same earlier? It was very difficult to find people in those times. How did he come to Cambridge University?
Well, he came to Cambridge University because Hardy had invited him to come. I mean, in 1913, as I mentioned in my lecture, 1913, he writes to Hardy, and there's a correspondence that between them for more than a year, at least half a dozen letters between the two of them, and then finally he's invited to come so that they can talk face to face, because it is, in those days when there was no email nor Zoom conferencing, it's very difficult to, even now actually, it's very difficult to do research with Zoom. There's something, as I said, there's something about the human being who is a social creature. And something, so now we can come back to this deity question again, something we don't understand. the interconnectedness of human beings. There is something when I see a person face to face and we're both excited in person, we feel inspired to do more.
Yeah.
Whereas if we are remote, we're not. And so that's somehow I think the real reason why Hardy invited Ramanujan. And then the other aspect of it was Neville, who was from Trinity College, was going to India. And he said, well, why don't you go? You're going exactly to this place. Why don't you check this guy out, convince him to come? And that was the opening. And I think that's the reason why he did that.
Yeah. Yeah. So the next question from Nancy Moria is, can a multiple and factor of a number be negative?
I don't know. Multiple and a factor of a number be negative. What does that mean? Don't know.
Well, can it have a negative value? That's, I think.
So when we talk, well, it's a question of when we talk about factorizations of natural numbers, we're usually talking about positive numbers.
Yeah.
And so that's basically what it is. Yeah.
Yeah, that's right. So then we have another question from Vinay. It's really amazing lecture. Thank you so much. Dr. Srinivas Ramanujan was an extraordinary man. His early work includes magic square. Did he make a magic square on his own date of birth?
Well, I don't know the answer to the last question, whether he made a magic square for his own date of birth, but he certainly was interested in magic squares early in high school, and he was playing around with them. You can see that when you check his notebooks. But magic squares are actually special cases of what are called Latin squares, and Latin squares are very important in both combinatorial problems. And in fact, if you look at your Sudoku puzzles, Sudoku puzzle is a Latin square. Basically, it's kind of the horizontal row, all the numbers, and the vertical things are also there, and then of course these separate things. So there are these kind of combinatorial configurations as being important. Perhaps he had an intuition of that when he talked about magic squares.
Yeah. This where I would like to add a point. He did actually make a magic square on his own date of birth, particularly his birth year. That's actually there in his first notebook.
Okay.
I mean, one of the magic square that he does in notebook 1, when he lived in Kumbakonam, I mean, he did make one on his own. I mean, that was something which amazed his friends and others.
Thank you.
Yeah. There is another question that comes is that can we find the secret of the universe by mathematics? I mean, I suppose what that person means is that essentially looking at science and nature, I think, which you had discussed earlier. But in case if you want to add some more, you can add on that.
Yeah,
or else we can.
I could certainly. I think that's a good question. I mean, the reason that anybody is doing science or mathematics or even art or whatever, I mean, if you you're trying to understand some aspect of the universe. I mean, so there's no way that one particular subject can encompass the whole secret of the universe in one thing. However, mathematics is a tool, just as medical science is a tool. Maybe there's a marriage between medical science and mathematics, as we're seeing with these models using probability theory to describe the movement of the virus, for example, right now, and trying to predict how to control it by using some mathematical modeling of the virus. I mean, so that's in that sense you can. So the idea of using mathematics to control life a century ago, people succumbed to all sorts of diseases because they didn't know about vaccinations, and you could actually control these. I don't know if many of you know this, but the first Nobel Prize in Medicine in 1902 has to do with malarial research that was conducted in Bangalore, India by Ross. And he was trying to describe a mathematical model to control malaria. And he came up with a perfect model for it. And he knew that by certain controlling of certain parameters, he could actually bring the malaria under control. So there's a marriage of mathematics with medicine. And I believe he got the 1902 Nobel Prize for this work.
Yeah.
So there's this aspect. So literature is not something that it also tries to tell you something about the universe. So the universe cannot be kind of encompassed in one framework. No matter what framework you pick, it will not. But all of these frameworks, and probably many more yet to be discovered, can be used to enhance our understanding.
Okay, so there is one question which, of course, one would expect any lecture on Ramanujam when wide variety of audience are there is Hardy Ramanujam number.
What does that mean?
1729.
Yeah.
No, they want to know why that is significant, in a sense.
Well, in some sense, every number is significant. that particular number happens to come in the context of the Tau function and the theory of modular forms. And then I was trying to make a little joke by telling you that it actually appears in the Kurma Purana. And it does. And it comes in the context of the number of seconds that the mind has to be focused on an idea in order to get enlightenment. So there's this, connection with numbers in the Puranas as well. So all numbers are significant in their own way. Nothing special about 1721.
Right, sir. That's a very interesting point, and that's where I think we need to wind up this lecture. We had a very wonderful lecture and a long one. I would request Dr. Ramanujam to say final words, and then I will ask our director to say the last word. I mean, Dr. Ramanujam, please.
Yeah, no, I just want to thank Ram for a wonderful lecture. Thanks very much. It's
welcome.
Inspiring and great to hear the lecture on Tau function. Hope for more opportunities, and soon, hopefully, after all this, we'll have you back in Chennai and lecturing to us.
Thank you, Dr. Ramanujam. May I request our director, Dr. Nakul Parasar, to say a word of thanks to the speaker and also wind up today's lecture.
A very interesting lecture, and thank you so much, Professor Murty. Very captivating, I guess, for everyone. And the kind of questions that came up did show. We've got a long list of people still writing and trying to ask questions, paucity of time. However, we appreciate everybody's presence here and would like to thank everybody who joined us to make this Ramanujam Yatras, this edition, a successful one. Once again, on behalf of the entire organizing team, may I express my gratitude and thanks to Professor Ram Murty, and also to our team here, Dr. Venkateshwaran, Dr. Ramanujam, Sri Kumar, and all others at the team here in India. With this, thank you so much once again, and I hope you all stay safe. And Dr. Professor Murty, you have a great day.
Thank
you. For all others here in India, a great evening, great night, and stay safe, stay happy. Thank you so much. Jai Hind.
Thank you. Thank you all.